All right. Hello, everyone. It's very nice. Hi. Very nice to be here today. My name is Kevin Brodsky. I'm a software engineer at ARM. Sorry for that. Today I'm going to talk to you about something that I think is quite exciting and not too evil, I think. I'm going to talk a little bit about security. But first, to get very concrete right away, let's look at this little example of how things can go wrong. So we have a function. It just does something. It just takes some input, writes to some output pointer, and there's something wrong with this code. Shouldn't be very complicated. What's wrong with this code? Okay, yes, maybe. We'll get to that. Anything else? Yeah, right. So out is too small. Exactly. So we're just, allocating 4 bytes for out, and we're allocating 4 times 4 ins for in, so 16 bytes. So, well, all right. Let's talk 64-bit today. Even 42-bit is fine. So yeah, here we're going to have a problem. Clearly, we're going to try to write to something we haven't allocated, and then it kind of looks like that. Just writing somewhere. Now, the interesting thing is that it's not really clear what's going to happen here. We might get a fault, we might not. Might overwrite some of our allocation, maybe not. We might never figure out, in fact. So that's kind of the issue with just C and C++ in general, is that they're memory unsafe by design, and pointers can kind of read and write anywhere. Of course, it's undefined behavior, but it doesn't mean that it's going to be prevented. There are, of course, many existing mitigations, both static, like sanitizers, and dynamic, for instance, stack protector. But so none of those is both comprehensive, either in detection or in prevention, or deployable in production, meaning very low cost. Obviously, yes, there is the path of rewriting everything in Rust, and Rust is very nice. I'm not arguing with that, but yeah, rewriting all the existing code is pretty tall order, I think. So it's a good idea to explore other ways to make C++, a little bit less unsafe. So really, from the previous example, it kind of makes you feel like it would be kind of nice if pointers kind of knew what they could do and where. So if I don't know if you can see my pointer. Yeah, exactly. So it would be nice to kind of know what the bounds are, so what the pointers can actually do, where. Also permissions, so can you read and write for a heap allocation? And yeah, whether it's valid, whether it's actually a pointer at all. So if we had that, then trying to access the previous access would just have been prevented right away. Well, it turns out that's exactly what a capability is. So a capability is kind of like a hardware concept. It's a 129-bit object. And it has this, so an address, of course, but then it has this extra metadata, like the bounds, permissions, and tag, which match this, and this, pretty much. And so capabilities can be used like pointers and dereferenced, and if metadata does not agree with what you're trying to do, then it's going to fault. So there's a few interesting properties with capabilities. So an important one is this tag. So this tag is a little bit magic. It cannot be forged. The only way to get a valid capability is to derive it from another valid capability. So that's this idea of provenance. You update capabilities through a chain of valid operations. And another important property is monotonicity. And so that's the idea that when when you do this derivation of capabilities, you can only restrict the bounds, so remove permissions or keep them, but you cannot add them. You cannot make a read-only pointer read-write. So, what is the context of all this? So the first part is Cherry. So Cherry is a research project that has kind of revived the idea of hardware capabilities. It was started a bit more than 10 years ago now, and so that's led by the University of Cambridge. And the way it works is that it extends an existing architecture, and nowadays mainly working on RISC-V, so Cherry RISC-V. And I think it's worth mentioning here that there's already an extensive software stack, like done by the Cherry research team, that's called Cherry BSD, so based on FreeBSD. Come back to that a bit later. Now, the reason why I'm here today is that ARM is leading another research program called Moredo, which includes this Cherry-like prototype architecture based on the ARM architecture. I'm insisting on prototype. It is not a product. It is an experiment. But the very important part is that it includes a board. So we have a quad-core prototype board that's available now, and that's what the SoC looks like. And this is quite based on high-performance ARM implementation. And this is the first silicon that actually implements Cherry concepts, so that's quite exciting, and should allow us to get realistic performance figures. I think it's also worth mentioning. So Cherry is not just about memory safety. It's also you can do more than this with capabilities. You can do compartmentalization in process. I don't really have time to talk about this today, but if you're interested, definitely please ask at the end, or later. So in terms of memory safety, how do we use Cherry? Well, the most straightforward model is really the pure capability model, where we just turn every pointer into a capability. And yeah, I've included this diagram from the Cherry guys, because I think it just shows you just how many pointers there are in a process. So it starts from registers there, and then you get pointers, globals in the stack, in the heap. They all point to each other, and also the code is involved with things like PLTs, and so all of these become pointers and become capabilities, and they should have tight bounds and tight permissions so that you can't do anything with them and do things that you're not supposed to do with them. So what does that give us? Well, the first thing it gives us is something that's quite important for the Cherry guys. Is this referential safety idea that a pointer can only be obtained through, as I mentioned, a series of valid operations. So you cannot create them out of thin air. And yeah, you have pretty strong guarantees there. But yeah, what interests us more is spatial safety. So essentially preventing any kind of out-of-bound access. And that's something that this model gives us pretty much by design. And there is something also that's also very important. It's called temporal safety, so preventing any sorts of use after free. That's being worked on. That's quite experimental at this stage. So in Cherry BSD, so the FreeBSD based stack, there is some support for that. In Linux, we haven't got there yet. So I'm not going to talk about this today, but yeah, feel free to ask as well. So what's the impact on the software stack in general of trying to deploy that? Well, first thing is obviously we're changing the pointer size, so it's a new ABI. We have to rebuild everything to make use of pure capability. On the other hand, the actual impact on the vast majority of existing code should be, in fact, very, very minimal. Some code is going to be impacted, and that's because you now have to be quite careful when manipulating pointers. One reason is that you have to use the right types. We'll come back to that. You can't use long, int PTR, for instance, is what you should be using to store a pointer as an integer. And then you have to distinguish between address, which is still 64-bit, right? It's not a 128-bit architecture, and pointers now capabilities. Important for things like aligning down pointers, for instance. Alignment of pointers is also important. Capabilities must be self-aligned. So if you have some buffer that is not aligned correctly, you will probably get some problems if you try to put pointers in there. And obviously, assembly will need some updating if you have that. And yeah, so I have this diagram on the right, so showing just most code not really impacted. The system code more impacted. So libc is obviously going to have to support this new ABI and some changes, especially allocators, unwinder, things that do weird things with pointers, and especially allocate memory are gonna have to be changed potentially significantly. But that's not that much code, hopefully. And finally, there's the kernel, which we're gonna come to just now. And yes, having this new ABI means we have a new kernel user ABI, so that's the arrows here. Because obviously libc and other things will talk to the kernel, and they want to use capabilities to talk to the kernel, so the kernel should talk capabilities. So what does that mean a bit more specifically? So we have this new kernel user ABI, so Pro Capability User ABI, PCU ABI in short. So two main sets of objectives. One is just functional, just make things work, right? So if the user provides pointers, they need to be capabilities, and they need to be recognized as such, read as such, and so on. And the other aspect is that the kernel provides all the capabilities to user space. So yeah, we have to provide usable capabilities, valid bounds, and so on. For instance, when you do an mmap, you have to get a capability. Yeah, when you do mmap, in fact, the capability you get kind of allows you to own this memory range that you obtain. Then on the security side, there's kind of two very important principles on the design here. One is the principle of least privilege, which makes sense in this whole capability world. It's that we just want to minimize the bounds and permissions. We want to minimize what you can do with these capabilities you obtain. And the other one is intentionality. So that's the idea that when user space asks for an operation to be performed, the kernel should always do this operation using the provided capabilities, so that the kernel does not use its own privilege to do that. And that's a pretty strong mitigation against any kind of confused deputy attack. So yeah, we have a specification for this ABI that has matured over the past few years. We're working towards stabilizing it this year. Yeah, as the implementation progresses, it's kind of like this first proof of concept implementation. So yeah, what does that mean to implement that ABI in Linux? Just a few important points. So like the first point that you really encounter when you try to do this work is just you have to propagate these capabilities. So I have this diagram on the right. Just give you the idea that if you have a syscall that just passes in a buffer, and that buffer is now a pointer to capability to this buffer. Well, you have to pass through this capability from user space right through to the point where you actually do the copy to user, and yeah, that creates some interesting challenges. So the other aspect, as I mentioned before, you have to provide this capability environment. You have to initialize capability registers on startup, for instance, correctly, and most importantly, you have to do all this mmap family that deals with capabilities. And finally, well, it's a bit difficult to switch the entire world at once, so we want to keep support for the existing ABI, standard 64-bit ABI, so to have both on the same system. So I'm going to come back on kind of all these technical details a bit later, because first I think it's maybe interesting to talk about just where we are now. So we have this project. It's called Morello Linux. It's not a very inventive name. Sorry. And yeah, but I'll think about that. So it is hosted as a fork on the Morello GitLab. Yeah, on Morello GitLab, where we have, in fact, most of the Morello software in general. We have achieved, so this functional support that I was talking about before, we have achieved that at a pretty advanced stage. So we have support for this ABI, for the 64-bit ABI as compat, and that's running on both the board that I mentioned and also on the fast model, which emulates the board and allows you to run this on any Linux machine. So we support the vast majority of syscalls. Some are a bit more complicated, but we're getting there. And we support a selection of drivers, the issue being that some drivers need some changes to be capability friendly. So we can't build the entire kernel yet. We have to be a bit progressive with that. The security aspects are under development pretty much right now, so we're making good progress with that. And yeah, testing has been a pretty big aspect of that as well. So we're adding some Morello specific case self-tests, and we are running the LTP for now, the syscall suite, and we've got the vast majority of tests passing in both ABIs. So just talking a little bit about the rest, because that's not just the kernel, obviously, which is also hosted on Morello GitLab. So in terms of toolchains, we have Clang, and we also have now Morello GCC. And in terms of like libc, C++, so we've spent a lot of effort on Muscle, but we also have glibc. There's been also work on Android in general, so there is Bionic. And yeah, so libc++, part of LLVM, to use with Muscle. And in terms of environment, that's where things are a bit more recent, of course. So for now we have just BusyBox as a baseline, so pure capability BusyBox. And there is a community effort to develop a Yocto layer called Meta Morello, which allow you to have a Yocto distribution, pure capability Yocto distribution. I just want to mention as well that it's not. The work has been done on this before as well, thanks to CherryBSD. So on CherryBSD, they have a collection of about 9,000 packages that are already building and running in pure capability. Of course, it's FreeBSD, it's not Linux, but that's a very good start, in fact. And what they found while doing this is that on average, they just have about 0.026% lines of codes that need changing to be pure cap friendly. And of course, sometimes that means, in fact, fixing bugs. Quite often that can mean fixing memory safety bugs. So that's the good thing with porting all that, we just find bugs. So, yes. What is important when porting, when having a new API or new architecture? Of course, it's Doom. So we have these guides now on our website. The first one allows you to set up an environment, so Docker environment. You can run that on pretty much any machine. Set up in just 10 minutes, and you get just a vanilla standard 64-bit distro plus a pure cap root file system with BusyBox. And that's running on the fast model, so you don't need to have a port. And yeah, so we have this SDK that allows you to build and run some software in pure capability, whatever you want. So for now, just C, but then C++ is coming. And yeah, we have pure capability Doom running on the Morello board. So yeah. This project is now really fully open, so we're trying to do everything in the open. So we have this mailing list where we just post all the patches. We can have all discussions, all kernel-related discussions there. We have task tracker as well. You can get an idea of where we are, what we're going to do, who does what, and yeah, quite importantly, we have CI that's running. tests on actual Morello boards. So that's like building the kernel, booting the kernel, and then K-self test, LTP, and muscle test as well. And that's not just for this main repo that I mentioned. That's in fact all developers registered on Morello GitLab can request to be able to just run the CI against their patches. Yes. So I have a bit more time. So maybe I'll talk a little bit more about how does this actually work. So there are two strategies to implement this Visual Space ABI in the kernel. The most obvious one is, well, just make the kernel pure cap, just same ABI, simple. So you just turn all the pointers, kernel pointers and user pointers into capabilities, which of course has security benefits too for the kernel. Now the bit of a problem is, as I mentioned, representation of pointers becomes interesting. And on Linux, that's a pretty big problem because pointers are very, very often not represented with the right types, specifically long, very often. So porting that kernel to pure cap would really be a huge task, and it's not just the types either. It's also everything to do with allocators is quite tricky. So what we've decided to do as a first approach is more of a middle ground, so the hybrid approach, where we just make the user pointers capabilities. We don't touch the kernel ABI, and we use some compiler extension to turn user pointers into capabilities. And we have to be a little bit careful, of course, when manipulating those. So what does that look like in practice? So just like this is just like the handler for this get CWDC call that just gives you the current working directory. It's simplified, of course, but I've highlighted buff because here buff is a user pointer, right? And the important thing is that we want this to be a capability down to the point where it's actually used, not necessarily directly in the function. Of course, it can be nested. It might need to propagate, and the rest remains unchanged. So how do we do that? Well, it's nice because we have this _user annotation, so we can reuse that. It's used most of the time, almost always. Now even more because we fixed some of the bugs with that. In fact, some of the missing annotations. So we just redefine this annotation to be an __ capability, and that turns the pointer into a capability. It works most of the time. Sometimes it doesn't because of the position of the annotation. It's a little bit annoying, so we have to fix it up sometimes. But that allowed us to progress quite fast on this propagation problem without having to have huge changes in the kernel. And just in terms of how it looks like in terms of UAPI, so on the left, there's just like struct IOVEC in the UAPI header. So it has this user annotation. So in our kernel, it's going to expand to capability, so the IOV base becomes a capability. In user space, nothing changes because the user annotation just remains, well, it still expands to nothing. But in the pure cap ABI, this is already a pointer. So, sorry, this is already a capability, so that matches the kernel. And yeah, just to mention, the _ user annotation is still usable by sparse. We're not removing that. That's different matter. What is less nice is that _ user is not the only way to represent user pointers. Sometimes they're put in other things, especially they're often put in U64, especially in newer UAPI aspects. So typically clone-free or IOU ring, the entire subsystem, uses U64 to represent pointers. That's not nice because that doesn't work for us. So we have to redefine the structs essentially to use a new type that can represent capability. And that is backwards compatible, that doesn't affect other ABIs. And of course that means we need to have separate compat handling because the reason why it's a U64 to start with is that you don't have to do compat. It's the same size in any ABI, well now it's not anymore because there's no other way, really. So that's just change of the UAP header before after for clone args, so the clone free struct. Yeah. So how do we use the capabilities? Well, if we can, we just use them in EU access directly. So we just take the capability, dereference it, see what happens. If we get a capability fault, well, it's like an MMU fault, so we just abort and report -E fault probably. Sometimes we have to do explicit checks because user memory is accessed through kernel mappings. That's not as nice, but it's also common. And finally, sometimes we just give back the capability to user space. The user space just passes in a pointer, it wants it back, we give it back. That's the case for Seagull stack, for instance. And yeah, just coming back on what I was talking about with these root capabilities, that's quite a shift, because now we don't just have an MMU, we also have capabilities on top of the MMU. So to access anything in the address space, the process needs to have a capability. So we provide, to start with, for instance, this capability stack pointer allows you to access the stack. Same thing to access your initial code, so the capability program counter. But most of the time, really, you just get some new memory using mmap. So mmap gives you a capability with write bounds and permissions. And yeah, we have some new special entries for special cases, like for globals, you have to have a different way to get access to them. How much time do I have? Yeah, I'm just gonna say very briefly, 64-bit compat was interesting, because compat is definitely 32-bit idea to start with. Surprisingly, it works, and it works quite well. So we had to remove some assumptions that compat is 32-bit. But otherwise, yeah, we have to be careful with converting pointers again, because all compat pointers need to be converted to a capability. And we do some of that automatically, but not all of it can be done automatically. So a bit of fixing also existing code. Right, so to wrap up on all this, if you have to just remember a few things. So cherry capabilities is essentially, that's pointers made reasonable, not a smoking gun. And the pure capability model, it's really C, C++ with built-in memory safety. And we have so functional modular Linux stack. It's available right now. The security aspect still under development, but it is functional. And I think the important aspect is that this is really a starting point, so supporting pure capability. It's not easy, but it's a starting point, because with that you can do further things. So you can do, as I mentioned, temporal safety to prevent use after free. And that's also very useful for all things related to compartmentalization. So having different compartments in the same process with strong isolation. So if this sounds interesting, well, please give it a try and get in touch. And it's, as I said, it's a fully open project, so contributions are more than welcome. And I just want to conclude on some credits, because this was a pretty big team effort. And I'm really quite impressed with what we've achieved in the past few years. And yeah, that's what I had. Any question? That's fine.
The one thing is, I'm a little sad that you didn't try the conversion of kernel space itself, because that to me actually sounds like the more interesting project. I mean, user space, we have all kinds of great isolation methods that can isolate untrusted code. In the kernel, it's really hard, and the capability model would really help a lot. And I know you mentioned there's a lot of stupid casts to unsigned long. Well, getting rid of all of them would be good, even without the capability-based architecture. So while that might be a big project, I think it's a very useful one.
I agree.
Yeah.
So, yeah, to be clear, the reason why we went for the hybrid approach is, well, you see how many people we are. But most people didn't work full time on this, right? With very resource constrained. So we just wanted to get somewhere. Clearly, it's quite clear that the pure capability kernel is where we want to get. We just need people like you, maybe,
Right.
to help us on this way. I mean, upstreaming this is obviously going to be a huge challenge.
Yeah,
so-
and that brings me to my other interesting question. So, well, we tried actually two little ones. One is you said you want to store a pointer in an int pointer t and not a uint pointer t. Why do you need the sign bit?
uint or int pointer is the same thing.
Okay.
It's about the size. It's about the type.
No, I know it's about the size, but you mentioned the int pointer, and that always seemed like a really strange representation for the few cases where it even makes sense to store a pointer in a scalar, which rarely does. But
think uint PTR.
yeah,
Think
okay.
uint PTR.
And when we tried to use uint pointer a little more in some Linux subsystems, Linus Torvalds got really angry at us and used unsigned long because no one's ever going to make it bigger.
Yes.
Are we going to have a fun flame war?
So that is actually a very good point. There was some interesting threads with Linus Torvalds and Arne Bergman as well. We need to have new types.
Yeah.
And I mean, uint pointer is probably not quite the right answer depending on how you approach it. We need to have new types. We need to have these discussions.
Yeah. And I mean, I think the answer to 95% of the problems is don't frickin' cast it to an integer to start with, but that's not going to solve everything, but a very large part of it.
Yeah.
And I mean, the other interesting thing I thought of is there's a lot of hardware interfaces or things you can't touch where you have a 64-bit cookie where life gets a lot easier if you can smash a pointer in there. And I wonder what a good way to figure out how we can get a capability in there or get from a 64-bit pointer to a capability in a somewhat verified way. I mean, the one thing I'm thinking of, for example, is like InfiniBand RDMA hardware where each completion queue entry gives you 64-bit of specific data. And it's very, very helpful if that's a pointer.
Yeah, so actually, I mentioned IOU-ring. That was an
same idea, yeah.
Yeah, so that is the same thing. So we've actually done that work, and you have to change the entire layout to put capabilities in there. Now, of course, if you have hardware,
if it's hardware, we can't easily
exactly.
change the layout.
So if you have hardware, then it's obviously much harder.
Yeah,
and
I mean, either you do something like an IDR allocator or X-array or whatever we use in the kernel that gives you a small integer, but that's, of course, quite a price to pay. And I just wonder if there's any good way to figure out that you can convert, say, look into hardware extensions that get you a pointer, and as long as that pointer is in a known good list or whatever, can actually turn that into a capability in a semi-verified way?
Good question.
Okay, I'll shut up now. I'll let others talk.
So my question is, what's the performance impact, if any?
Yeah, of course.
I'm curious, right? I don't judge, but
no. I mean, it's a completely fair question. I mean, and this is of course a pretty big part of the model project. So I don't really have numbers because there has been a lot of work actually happening in the past year or so on performance, and I believe there is a paper that's going to be published very soon. So it's a collaboration between University of Cambridge and ARM on this. The reason why it's taking quite a long time is that, as I mentioned, the Morello hardware, so the cores are high performance. They're based on high performance A-profile cores, but they don't necessarily the best possible implementation, which is quite normal for a research project. And we're trying to understand why some numbers are not as good as they might be before we, maybe give the wrong idea.
Yeah.
So yeah.
No, I completely understand that.
Yeah.
But I mean, I guess you could at least have a baseline comparison, even on the same hardware with, given that you retain the 64-bit ABI.
Sure,
then
absolutely.
you can at least compare apples
Yeah.
to apples with and without the capabilities. I mean, essentially, just the fattening up of the pointer should have some impact. So
Yeah, it has impact for various reasons. So, I mean, it's mostly one, you have to do more to just check the capabilities and all that. But also you have a memory impact, so you just use more memory, and that has interesting implications. Yeah. Cache line. Yeah, right,
Yeah.
exactly. So for instance, like I mentioned IOU ring again, now the IOU ring SQE is twice the size.
Yeah, instruction caches I would expect also
Yeah.
to be impacted.
So various impacts, yeah.
Looking forward to the paper.
So first a comment. So that sounds a lot like Java arrays.
Like what, sorry?
Sounds a lot like Java arrays.
Java arrays.
You have a pointer, you have a length, you can't go outside it.
Yeah.
You have a validity with a.
Yes.
So my question is about, I guess, the hardware. How do you manage these pointers? Do you have special registers, instructions for offsets and narrowing and stuff like that, or? How does that work?
Yeah, that's a very good question. So broadly speaking, in the hardware, you just extend kind of everything. So the registers just become literally 129 bits. And then everything else, so like cache lines also get extra bits for the tags. Of course, in memory, it's a bit harder to just stuff that additional bit next to the memory. So there's two approaches. One is you just allocate some memory for the tags, and then you have some sort of splitter that splits the request between data requests and tag requests, and then just combines. Or you can use ECC bits essentially to store the tag. And so the Mortar board interestingly implements both of these approaches, which allows us to do some interesting performance investigation of that too.
And manipulation of the capabilities, is that special instructions or?
New instructions.
New instructions, yeah.
New instructions. So it's okay. Maybe not go too much into details, but there are two modes in the ISA in Morado. So there's one mode where essentially your base register for any load and store becomes a capability. So you just have all the load and store instructions that can be capability based. And then you have some more instructions to do things like setting bounds, setting permissions, and all that.
Okay.
It's not that many, actually, new instructions. Yeah.
Okay, thanks.
Yeah. Wow.
So, talking about those instructions, do you have some, like for higher level code, some API or annotations to say like, okay, to manipulate like a capability to say like, okay, I do a big allocation and maybe I want to divide that allocation into two and then have separate capabilities for each parts?
Yeah, that's also a very good question. So, I think the first thing to say is, like when you build software in pure capability, most of the time you don't do anything, right? It just works. Because there's a lot of magic happening with a compiler, with the whole runtime. Obviously, some software needs to do some operations. So there is a fairly, I would say, minimal API existing. Is some cherry header that gives you macros that do things like cherry bounce set, cherry perm set, getting the address. Well, all these things. We don't really have any standardized higher level API yet. I think it's probably going to end up being more OS specific.
Okay.
Yeah.
Okay, that's quite interesting because I don't know if you're familiar with the work because it has just been posted maybe 8 hours ago in the.
then no.
like just yesterday evening. I was reading a post in the LLVM community about a patch set that is called -f bounce -safety.
Okay.
And they solve the similar problem, like on a software level only, by introducing, but just doing a lot of bounce checks and annotating the existing source code with attributes saying, like, for example, this size corresponds to that pointer and so on.
Right.
And they also talk about how they, extend the ABI to support passing like a pointer with a size and so on. So maybe that is something
that sounds interesting
to look into.
Yeah.
I'm not sure whether you can reuse anything, but I think it's a completely different approach, but I think there is some intersection between the two
Yeah, but that
things.
sounds very interesting actually. I will look into that.
Yeah. I will just double check. I think it's called F-bound safety.
Okay.
Or not F-bound
Uh,
check.
uh,
F-bound safety.
Advanced
Yeah.
safety. It makes me think actually on this topic that there are discussions to upstream the Cherry LLV, so some parts of Cherry LLVM. I don't know where this got, but it's like all things with Cherry, the issue is that it's a pretty big change, and starting soon is better than starting late.
Okay.
I mean, the other interesting question I have is just about the amount of extra information we need, right? So right now, you basically, well, double, slightly more than double the size with a
Yeah.
tech bit. And how many objects that we have a capability for actually need a 64-bit length?
64-bit length. I'm not following.
I mean, your bounds. Why does your bounds have to be so big?
Okay, right. So let me get back to that, because actually they're not. Yeah. So
Oh, we have the permission bits. Okay, yeah.
yeah. So that's the thing. The first capability format was 256-bit, right? That was when Cambridge Uni started on that. They had full precision bounds, right? And yeah, that didn't fly so well for some reason. So this is actually a compressed format. That's actually, the maths here are fairly complicated, but essentially you get full precision for ranges that are fairly small, right? I don't know. I don't want to say something stupid, but okay, like a few kilobytes, you can have full precision. Then above that, you will have constraints on what you can represent. This creates some very, very interesting problems when you talk about mmap, for instance. But yeah, that's. I think you can't do much better than that in terms of format.
Okay. Okay. It sounds like, I don't know, hardware architects might try to squeeze out a bunch more bits. I mean, similar with the address, right? I mean, are you really going to use full 64-bit addressing, because the high bits are usually used for other little tweaks, like MTE or...
So I think the answer to that is there's no hope on the address, because ARM now has support for 52-bit VAs. And the top byte is already in
Magic,
the Linux
yeah.
ABI reserved, because it's ARM64 has top byte ignore, so you can do anything you want with it. Things like MTE, memory tagging, use that.
Yeah, that's what I said.
You could combine MTE with that, maybe.
That's what it is. I mean, it's kind of exclusive, right? If you do capabilities, you don't really need MTE.
Well, not necessarily, because so MTE is much more, well, it's about both temporal and spatial safety, but it's really good for temporal safety,
Okay.
which is, and temporal safety is not so easy with capabilities. So there is potential here.
Sounds all much more complicated than my term paper 15 years ago, where I decided I don't need a capabilities architecture and just abuse x86 segmenting. But
Yeah. Real life is complicated. I think we're out of time, are we? Yeah. Yep. Yeah, thank you very much.